Lesson: Backpropagation and Gradient Descent Algorithms. Backpropagation and gradient descent stand as cornerstone algorithms within the field of advanced neural networks, enabling the effective training of complex models by minimizing error rates. Understanding these algorithms is essential for professionals aiming to implement artificial intelligence solutions in real-world applications. This lesson delves into the mechanisms, practical applications, and the integration of tools and frameworks that facilitate the proficient implementation of backpropagation and gradient descent. Backpropagation is a supervised learning algorithm used for training artificial neural networks, crucial for the fine-tuning of weights to minimize error and improve the model's accuracy. It operates by propagating the error backward through the network layers, adjusting weights based on the gradient of the loss function concerning the weights. This process ensures that the neural network's predictions become more accurate over time by optimizing the weight parameters. The algorithm involves two main steps: forward pass and backward pass. During the forward pass, inputs are fed into the neural network and predictions are made. The difference between the predicted and actual values is calculated using a loss function, commonly the mean squared error or cross-entropy loss. The backward pass begins with the computation of the gradient of the loss function with respect to the output layer's weights. This gradient is then propagated backward through the network, layer by layer, updating the weights using the chain rule of calculus. The essence of backpropagation lies in the iterative update of weights to find the optimal set that minimizes the loss function. The implementation of backpropagation in practical scenarios often involves frameworks such as TensorFlow and PyTorch, which provide robust libraries for automatic differentiation and gradient computation. These tools simplify the process of building and training neural networks by handling the complex mathematical computations involved in backpropagation, allowing practitioners to focus on model architecture and hyperparameter tuning. Gradient descent is a first-order optimization algorithm used to minimize the loss function by iteratively moving in the direction of the steepest descent, defined by the negative of the gradient. The basic idea is to update the weights in the opposite direction of the gradient, scaled by a learning rate, which determines the size of the steps taken towards the minimum. The choice of learning rate is crucial. A value too small can result in a slow convergence, while a value too large can cause the algorithm to overshoot the optimal solution. There are several variants of gradient descent, including stochastic gradient descent, mini-batch gradient descent, and momentum-based methods, each offering different trade-offs between convergence speed and computational efficiency. SGD, for example, updates the weights more frequently by computing the gradient based on a single training example at each iteration, which can lead to faster convergence in some cases. However, it introduces noise into the gradient estimates, which can hinder convergence. Momentum-based methods help overcome this by incorporating a fraction of the previous update into the current one, effectively smoothing the trajectory of the iterations and accelerating convergence, especially in the presence of ravines in the error surface. Practical application of gradient descent in neural network training is supported by popular deep learning frameworks. TensorFlow and PyTorch offer built-in optimizers that implement different variants of gradient descent, allowing practitioners to experiment with and select the most suitable optimizer for their specific problem. Real-world challenges in neural network training often involve issues such as overfitting, vanishing gradients, and computational inefficiency. Overfitting occurs when the model learns the training data too well, capturing noise alongside the underlying patterns, resulting in poor generalization to unseen data. Techniques like dropout, regularization, and early stopping are commonly employed to mitigate overfitting. Dropout, for instance, involves randomly dropping units in the network during training, forcing the model to learn more robust features. Regularization techniques such as L1 and L2 penalties add constraints to the loss function, discouraging overly complex models. Vanishing gradients, a problem where gradients become exceedingly small, stalling the training process, are addressed by using activation functions like ReU or employing architectures such as LSTM and GRU in recurrent neural networks. These techniques maintain a more stable gradient flow, facilitating deeper network training. To enhance computational efficiency, practitioners leverage parallel computing and hardware accelerators like GPUs and TPUs, which significantly reduce training time. Frameworks such as TensorFlow and PyTorch are optimized to exploit these hardware capabilities, making the deployment of large-scale neural networks feasible. An illustrative case study is Google's application of deep learning to improve the performance of its search engine. By employing neural networks trained through backpropagation and gradient descent, Google enhanced its ability to understand search queries, delivering more relevant results to users. The use of frameworks like TensorFlow, developed by Google, allowed for efficient handling of complex models and large datasets, showcasing the impact of these algorithms in a real-world context. Statistics further emphasize the significance of these algorithms in practice. Research indicates that the use of advanced optimization techniques, including momentum and adaptive learning rates, can improve convergence speed by up to 10 times compared to standard gradient descent. Such improvements are critical in industrial applications where time and computational resources are limited. In conclusion, backpropagation and gradient descent are fundamental to the training of neural networks, providing the means to optimize model parameters and achieve high accuracy. Their implementation is facilitated by powerful frameworks like TensorFlow and PyTorch, which offer the necessary tools to handle the complexity of neural network training. By addressing challenges such as overfitting and vanishing gradients, these algorithms enable the development of robust models capable of tackling diverse real-world problems. Professionals equipped with this knowledge and practical understanding of these algorithms can enhance their proficiency in AI implementation, driving innovation and efficiency in their respective fields.